The p-value. Many researchers make it central in the way they think about their data and make their research decisions. But should we trust it? One interesting thing is that the p-value has hardly been studied. We know very little about how researchers actually think about and feel about p-values. Great topic for research. So let me speculate. I think that usually people think about p in terms of intervals like this. So p less than 0.001, 3 stars, all the way through to p greater than 0.10. And think of p as a measure of strength of evidence. And this elicits significance language from very highly significant down through here, and values between 0.05 and 10 approaching significance. How do you know it's not running away from it as hard as it can go? And we want this language to indicate truth. We desperately want to know about the world and know about truth. There is an effect, or there is no effect, or perhaps even a zero effect. And this evokes emotion. P has affect attached. And it really matters. People make decisions in the world based on values of P, whether you get tenure or not. And so it's central in everyone's thinking about research. But should we trust P? Let's think about P and replication. If P reveals truth, surely if we did the experiment again, it should reveal the same truth. If we get P 0.05 and repeat, of course we wouldn't get exactly 0.05, but what would we get? Something in 0.0406 or 0.0307, or should we think about an even wider interval? Well, let's do some simulation and investigate. I'm going to take a very standard sort of experiment, 2 independent groups, each of size 32, so a control group and an experimental group. And here I'm assuming there's a control population normally distributed of, say, well-being scores, which has a mean of 50. And the experimental group, let's suppose they've had your skillful massage for an hour, and on average this has increased their well-being score by 10 points. These normal distributions we're assuming have standard deviations of 20, so that's an effect size in the population of 10 points, or 10 over 20, that's 0.5 of a standard deviation. Cohen's delta of 0.5, or standardised mean difference of half a standard deviation. So let's run an experiment, and the 32 blue dots are our 32 people who read the magazine instead of having the massage, and there's their mean and 95% confidence interval. The 32 red experimental scores and their mean and confidence interval. Let's turn on a difference axis there with a 0 lined up with a control mean, and this experiment estimated the difference, the advantage of the massage, at about 3 points. And there's the difference on this differences axis there, and here's the confidence interval on that difference. Let's do the experiment again, and that first result drops down, and this next experiment estimated a difference of about 5 points. And this next one about 11 points. And if we run this experiment a number of times, exactly what we expect happens, and these means and confidence intervals bounce around, the dance of the confidence intervals. Now remember, of course, in real life, we don't know the populations, and we know only a single one of the experimental results. And so we have to imagine in our mind's eye some populations and imagine these confidence intervals bouncing around. But does this single confidence interval tell you something about what's likely to happen on replication? What the whole infinite sequence of bouncing around results will be? Yes, it does, because the width of the confidence interval gives you, the width of any of these confidence intervals, gives you quite a reasonable idea of what the variation in this whole sequence is, the bouncing around. So a confidence interval gives us quite good information about replication. Now let's think about the p-value. We're going to run an experiment, there it is, and here is p. Let me turn on the histogram here, and I'm going to use little figures to represent the various p results we could get. So for example, if we get 3 stars, we get this little red trumpet dancing for joy. 2 stars, still very happy. 1 star, okay. That's the questionable one, and you don't want to hear this, do you? There it is. Oh, deep depression of p greater than 10. Okay, our first experiment, our confidence interval just included the null hypothesis of 0, and so that means not significant. We'll get a p-value a bit greater than 0.05, and indeed we do, 0.095 question mark. Let's do another experiment, and this time the confidence interval overlaps 0 a bit more, so we get a p-value greater than 10, dark blue. Let's do another one, another one, another one, and now I'm going to run a whole lot. And let me stop it at some random point. Now, just to recap, here we have the dance of the confidence intervals, this bouncing around that is inherent in the definition of a confidence interval, what we expect and very informative. But look at these p-values. We've got everything from 0.8, 0.4, all the way down to 0.001. Everything from p greater than 10, blue, down to 3 stars, red. So if I did an experiment which amounts to closing my eyes and choosing from the screen a single experiment, the confidence interval will give you some reasonable information about this whole sequence, but the single p-value won't. If I give you just one of these p-values, what do you know about this whole sequence? Answer, virtually nothing. P tells us almost nothing about what's going to happen on replication. Let's, I'll turn off the sound and run this quickly for a while, and I'll build up here the frequency histogram of the different p-values we get. Up at the top here, you may be able to see these percentages. Theoretically, we expect about 10% to be 3 stars, 18% 2 stars, down to about 36% of the p-values, p greater than 10. And so there is the distribution of the p-values for this particular experimental setup. 2 independent groups of size 32 and a true difference in the population of half a standard deviation. Of course, if we varied that population effect size or varied the sample size, we get a different distribution of p-values. But the conclusion is that the distribution of p is very wide, no matter what experimental situation you have. And you can download this software and play around with it and satisfy yourself that my general conclusion does hold, however you set up the experiment. Let's look at it slightly differently. I'm going to turn on the p-value casino, because doing an experiment is really like going to the casino and spinning the p-value roulette wheel. Where will it land? Okay, I'm going to close my eyes. Here is the little figure bouncing around telling us where the ball is on the roulette wheel. I'm going to close my eyes and press stop. I happen to get 2 stars. Not bad. Might get that paper published. Let's run it again. Hold your breath and visit the p-value casino again. 2 stars again. We'll do it one more time. Uh-oh. 0.5 to 10. Very frustrating. And so we could go on. And every now and again we'd be unlucky and get p greater than 10. Sometimes we might be lucky and get, oh dear, 3 stars. And finally, the dance of the p-values. Over here we have the dance of the p-values down the screen, and I hope it gives another way of thinking about just how unpredictable p-values are. You could play this at parties. Develop a dance for the dance of the p-values and reflect on how ridiculous it is that p-values are right at the centre of our thinking about drawing conclusions from research. Far better to have confidence intervals because they're much more informative. And one thing they're informative about is telling us about what's likely to happen if we repeat the experiment. So the conclusion is that if you replicate the experiment, you're very likely to get a very different p-value. In fact, if your first experiment gives you p.05, then you need to look at an interval as wide as this, from 0.408 up to 0.44, to have an 80% chance that your replication p-value will lie within the interval. So there's even a 10% chance your p would be greater than 44, 10% less than this. Any p-value could easily have been very different. A p-value gives only extremely vague information about what's likely to happen on replication. The conclusion: don't trust p. The software I've been using is ESCI, Exploratory Software for Confidence Intervals. It's a free download. Please grab it and do some experimenting with larger samples, smaller samples, and so on. You can download it from this website, thenewstatistics.com, and there are other goodies as well. Perhaps I can mention my book. I'll probably mention it a few times along, which sort of gives a few clues or a bit further discussion about all these sorts of good things.